I'd like to talk about a new strategy for synthetic end caps to constrain peptides in helical conformation. And this arose from a bioinformatics study of ASX motifs. For those of you not familiar with ASX motifs, they're based on a side chain end cap to main chain N3 hydrogen bond interaction, where the end cap residue is the last one in a non-helical phi-psi orientation before the helix actually begins. The second hydrogen bond involved is a main chain end cap, main chain N4 interaction. I'll talk about how these are conveniently accessible end cap mimics, and they were designed from this bioinformatics study. So first of all, we designed a routine for searching ASX terms, then discovered a phenomenon that we called hydrophobic triangles, and out of that came a design for Bicyclic ASX Motif Mimics, or BAMs. Our database searching routine is called ASX ST Search. It derives from the protein databank. A key feature of this is that the database has all unique side chains. This allows for searching of ASX and actually ST motifs. The coordinates from each hit are downloadable, allowing access to dihedral angles and atom-to-atom distances. So armed with that searchable database, we went searching for features of ASX motifs. And the first one that we saw was a known one, and that's a hydrophobic interaction between the N' residue and the N4 residue side chains, illustrated here for isoleucine and leucine. Again, if you're not familiar with the side chain nomenclature here, please go back and watch our previous video. But out of that, we realized that hydrophobic triangles are often formed as well between N3, N4, and the N cap side chains. Nearly always, the N' to N4 residues are hydrophobic in the form that everybody would recognize them. But at the N3 residue, these can vary between glutamic acid, threonine, asparagine, aspartic acid, and serine. These are residues conventionally regarded as hydrophilic. So why do we call them hydrophobic? Well, the reason is those hydrophilic residues can donate a hydrophobic C-beta methylene, and that packs against, in this case, an N' leucine and an N4 leucine to give a hydrophobic triangle. It leaves the glutamic acid side chain outside of that packing to form hydrogen bonds. Well, what proportion of helical ASX motifs contain hydrophobic patches? And what proportion contain hydrophobic triangles? So a basic bioinformatics study shows that of all the helical end caps, 62% contain hydrophobic patches, and 29% overall contain hydrophobic triangles. Of course, every motif with a hydrophobic triangle must feature a hydrophobic cap. To test the relevance of this packing feature, we first of all did experiments with natural peptides, and we chose 17mers of this form because they were about 50-50 helical and not helical in PBS. And the 4 critical residues are shown in blue here. We can change these 4 residues in systematic ways to introduce different motifs around the N-terminus of the helix. So for instance, if we replace the N-cap residue, which is currently an alanine, with an aspartic acid, that forms an ASX motif. And that gave us a slight increase in Helicity in PBS, 59% relative to 52. If, as well as that, we change N' and N4 from alanine to a typical hydrophobic residue, and we find leucine and leucine is the best, the Helicity jumps to 74% in PBS. And then, if we incorporate an N3 hydrophobic residue to give us a triangle, in PBS, this peptide is 100% helical. So hydrophobic triangles definitely have an effect on the helical conformation. How can we use this knowledge to form a synthetic mimic? Well, let's review quickly 2 of the ways synthetic end-cap mimics are formed in the current literature. There are others, but they are mostly of historical relevance. One way is hydrogen bond surrogates, popularized by Aurora, who developed alkene metathesis reactions to give a hydrophobic side chain strap here that mimics a CO to NH hydrogen bond. There's another one by a scientist called Li in China, and what he did is he used an aspartic acid and he amide bonded it back to the N3 residue to give a peptidic strap. So we wondered if the 3 residues of a hydrophobic triangle could be replaced by something else that's hydrophobic. So our idea was to take out, say, the 3 leucines in this ASX motif and replace them, first of all, with cysteines. Well, that won't do, they don't pack. But of course, cysteine residues can be alkylated in Klip's reactions. And this symmetrical 1, 3, 5 bromomethylene aromatic is ideal because it doesn't matter which bromomethylene is alkylated first. That tribromomethylene benzene, TBMB, is converted to a trimethylene benzene on alkylation. And that, theoretically, would give us a bicyclic ASX Motif Mimic, or BAM. Molecular dynamics simulations of a BAM helix starting in a helical conformation shows that the tricyclic system enforces that helicity quite well. It takes a long time in molecular dynamics for this thing to unfold, and it never quite does. We can just watch that for a second. And then if we compare molecular dynamics of the hydrogen bond surrogate, you see that unwinds very quickly in comparison. That's because it's a monocyclic system, it's not as constrained. But our BAM there is still sitting in mostly helical conformations. This looked promising, so we made peptides with 3 cysteines in, and they alkylated very efficiently with TBMB to give us a synthetic hydrophobic triangle. Thus, we could compare the capped peptide, where the capped cysteines are in red here, with a control peptide that has an ASX turn and a hydrophobic triangle, but no bicyclo cap, and a totally negative peptide. And when we did that in PBS, the mostly allopeptide, the negative control, was only 19% helical. The one with the ASX turn, the hydrophobic triangle, and there, of course, the hydrophobic patch, was 32% helical. But the BAM was the best one in the series, 51%. In the helix-inducing medium, 20% TFA PBS, then the helicities increased across the board, but again, the same trend was followed, and the BAM was 100% helical. We did a Van Hoff-like variable temperature CD study to extract thermodynamic data. And in 20% TFE PBS, we got melting temperatures that increase from the negative to the natural ASX turn with the hydrophobic triangle to the BAM, both in terms of enthalpy and entropy. Then we took a 12mer and did a constrained NMR molecular dynamics simulation. First of all, for the natural peptide containing a hydrophobic triangle formed from leucines. That packs really nicely, and we clustered the preferred conformers constrained by the NMR constraints and selected the mean one here. So on the right-hand side, you see a space-filling diagram showing the packing. And then we did a similar NMR-MD study of the BAM. We had more constraints from this. And that is the structure of the BAM, and you can see the TMB group there is situated where the hydrophobic triangle would be. Really revealing, I think, was Ramachandran plots. So when we're looking at the peptide with an ASX motif and a hydrophobic triangle, the middle amino acids were dispersed in terms of the phi angle. But in the BAM, the cap system, the phi angle was more constrained. Looking at preferred conformers of the BAM and the natural peptide system, one would predict the NH of C4 would be shielded from the solvent. And if it was, it would be protected by HG exchange. So we did HG exchange experiments, and sure enough, there was protection for both systems, but the natural peptide didn't behave in an ideal way. The L4 residue was actually not the one most protected. But for the BAM, the C4 residue, NH, was easily the most protected in the series. So in conclusion, hydrophobic triangles were unanticipated because ASX terns have been known for 20 years. They have significant impacts on helicity. BAMs are the first bicyclic synthetic helical capping mimics. They're more rigid than other types of synthetic end caps. They're helix reducing, even in 12mers, which normally don't exist in helical conformations. Synthetically accessible, as much as any stapled system. And they're formed using inexpensive reagents that are non-toxic. So if ever a GMP synthesis was required, the methodology is suitable for that. N-terminal extension is possible from the BAM systems. It's not from hydrogen bond surrogates. And they overlay well on ASX terms. If you're interested in more research from our group, please search byinquisition on YouTube. Thanks everyone, and goodbye.